page 14, the parallel problems. I don't have the charts up, so I'll just like write the values on the circuit and you can fill them in. Let's just start off with the first one. So we got these three resistors in parallel, but now there's a capacitor in series with one of those resistors. So I'll use I can use blue to kind of indicate the so I'll write this down. So blue will be my first connected, right? Whatever the values are first connected, and I'll use black to indicate what is after steady state, because there's those two different charts, and then I'll write the capacitance in black, the capacitance stuff too. So when it's first connected, remember the capacitor essentially acts like a wire with zero resistance. So if it helps, one thing you can do is just redraw the whole circuit with like no more capacitor, right? Just draw a wire going straight down through it. If you can do that, that'll help you kind of understand, will the capacitor short circuit anything, right? Because if I put a wire through here, you just get a parallel through resistor situation going on, right? There's no wires short circuiting anything, and we'll talk about when short circuiting would occur with this one. But yeah, no wires. You know, if I add a wire right here, it's not gonna affect the circuit. So initially, this capacitor isn't really doing much. So I can just solve this problem like normally. I know that each thing, so each branch will get 10, a voltage of 10, right? Voltage equals 10, right? That's our parallel rule. And then I can really quickly use Ohm's law to figure out how much current they're gonna get, right? So if they're each getting 10 volts because of the battery, right? Because each branch has the same voltage of the battery. In this case, I can just use V equals IR, right? V over R will be 1/2 amp, so 0.5 amp. So I equals 0.5, I equals 0.5, and then 10 over 10 would be 1. 0.5 amps, 0.5 amps, and then I equals 1 amp. And then power you can do really quickly by just multiplying current and resistance. Let me think, sorry. So we'll have 0.5 to 20, so power is going to equal 10 watts. Same thing here, 10 watts because of the same numbers. And then, sorry, wait, no, that's not right. Power equals 10. No, I'm sorry, it's 5 watts because I'm doing 0.5 times 10. I'm doing I times V, P equals IV, so current times voltage. 5 watts, 5 watts, and then, wait. This doesn't make any sense at all. Oh wait, no, this makes sense. And this would be 10 watts. Sorry, these numbers are, I was just reading the wrong thing. Okay, so 10 watts, 5 watts, 5 watts. I'm pretty sure I had that down. Yeah, I had that down. So total power, well, you could either sum it up or you could just do the total current. The total current through the circuit would, right, if you think about junction rule, all the current joins up back here. So it would be 0.5 times 0.5 times 1. That'd be 2 amps. So I total is an equal 2 amps. V total is just the 10 volts. And then power would be 20 watts, right? And then 10 plus 5 plus 5. Or you can multiply these two. So I think that's all the values in there. Now let's do steady state. So steady state is now when, instead of drawing in a wire for the capacitor, you can draw an open switch. So the capacitor won't let any current go through. So if you imagine an open switch right here, this part of the circuit's not complete. No more current is going to go through this branch. So what are my values going to look like? Let me get my black marker if I can find it. What is that going to look like? So no more currents going through here, so it's just 20 and 20. So would it still be 0.5? I think it would still be 0.5 amps, right? Because it's still 10 volts, still 20 resistance, but it's now going to be 1.5 amps. So that works out pretty nice. 1/2 amps, 10 volts. So these are kind of the same actually for the steady state part. And then the wattage right now is still going to be 5 watts for each resistor. But now when you add them, you get 10 watts for the total. And that still works because 0.5 times plus 0.5, that's 1 amp for the whole. So I can say maybe I can say I final, right? The final total current is 1 amp. V final is still 10. That didn't change. And the total power, right? Power final is going to equal 10 watts or something like that. So yeah, that's kind of going to be the steady state. So now let's look at the capacitor. So for this one, right, it's 3 microfarads, right? What's going to be its voltage? Well, its voltage, think about this branch, it's going to be 10 volts, right? Because no more voltage is being consumed by this resistor. It's all going to this capacitor. It's 10 volts, right? Because of that branch, it's all receiving 10 volts. So yeah, when it's fully charged, no more current's going through here. So V equals IR, 0 current means 0 V. All the voltage is going to the capacitor. So to find the charge, you actually just need to multiply C and V. So if I say C, V, and then Q, so I know C is equal to Q over V, I can just multiply both sides by V. So 3 microfarads times 10 volts, that's 30 microfarads. The micro stays because micro just means 10 times 10 to the negative 6. All right, now my energy, I can just do Q, 1/2 QV, I should say. So 30 times 10 to 300, half that, you get 150 microjoules. So the equation there I used is U equals 1/2 QV. All right, cool. So now try out this one. It's really just the same strategy. When you initially start it, you can draw it as a wire. So you can see right here, if I made this a wire, yeah, great. It's just still like two resistors in parallel, I should say. But look right here, if I made this a wire, you have to see that it's actually going to short circuit. So there's 2 ways to think about it. There's 2 explanations for why if I put a wire in parallel with the resistor, it'll like short circuit and not cause the resistor to shine. First reason you can think about it is a path of least resistance. So if the current doesn't have to go through a resistor, it'll go around it if it can, right? Or, right, if this was less resistance, more current goes through here, but still some goes in there. But another way to think about it is the idea of parallel rules, right? If a wire is in series with or parallel with a resistor, it still has to have the same voltage difference across it, right? So if current goes through this resistor at all, that would mean there's a certain potential drop, right? Because V equals IR. But that means that this path needs to have the same voltage. But if we think back to V equals IR again, the resistance of a wire is 0. So the only way for them to have the same voltage is if the current going through the resistor is 0. Because then voltage equals 0 because there's 0 current, and the voltage here equals 0 because there's 0 resistance. That's another way to think about it. So if you were to, so this resistor you can essentially ignore for this first part of the problem. And I know I'm going against my my stupid little key code here, but it's fine. Let's just do this problem. So now it's not too bad, because what I have to do actually first, I have to find the equivalent resistance. So 30 and 50, what is the equivalent resistance? It's 18.75, so I can use my parallel rules, right? 1 over R equals 1 over R1 plus 1 over R2. So I can make an equivalent resistor there, which is going to be 18.5, so I can draw it like this. 20 ohms, 18.5 ohms, or 7.5 ohms, and then I can put them in series again. So 20 plus 18.75 is going to equal 38.75. So 38.75 is the equivalent resistance. So the total current is going to equal just 10 volts over 38.75. Okay. Ohms. I think that equals to about 0.258, I think. 0.258. Pretty sure. That's what I wrote down. And now I can be like, okay, yeah, this current, that's the current going through the 20 ohm resistor. The current here splits, so you would have to think, okay, well, I know that if they have the same voltage, and well, how do I find the same voltage? Well, what I can do is it's just going to be the voltage of the 10 volt minus the current. So it'd be like, okay, so I'll call this V2. So this is just loop rule, really. The voltage of the battery minus IR for the voltage by the 20 resistor or 20 ohm resistor is going to equal minus V2 equals 0, right? Because if you think about that loop, I can add V2 to both sides, and I can solve for V2, right? Because I solve for the current going through this resistor. I know the resistance. I can get the voltage. Whatever that voltage is, it's going to be the same for both, but then you can divide, right? So if it's, I think my voltage was, so when I did that, I got like around 4.8 volts. So I can just do 4.8 divided by 50 and 4.8 divided by 30. So I got 0.61, 0.161, and 0.09, something like that. I can show you if you want. Here, you can see. I'm really just doing now this stuff isn't really that new. This is just what I've just been doing. Like, it's not or not what I've been doing. I don't know what I'm saying. I'm so tired. It's not like anything new. It's just what we've been doing, like in terms of the resistance unit. You're just finding the equivalent resistance and finding the current going through each element. When the capacitor is fully charged, now you put an open switch. So if you, sorry, I had my voice. You have an open switch here. No more current's gonna go through this one. So this is our equivalent resistor loop, right? Or not equivalent resistor, sorry, but the path of the circuit. It's just gonna be these three resistors. Equivalent resistance, you could do 20 plus 30 plus 20. That's 70 ohms. So my total current is gonna be 1/7, I think. Sorry, it's 10 over 70. So yeah, 1/7, 1/7 amps, right? Or something like that. Equals current, or I. So that's the current going through each resistor because it's in series. And then to find the voltage, you just take that current, multiply it by each one. That part's not too hard. The key new concept is understanding that when I have a capacitor, it can either act as like a closed switch or an open switch, or like a wire and an open switch, whatever. That's kind of the hard part. And then I can also show you what I put down if you need it. If you just want to like hopefully check your work. There. Yeah, there it is. All right, I can quickly do the capacitor stuff. Really key idea, right? Is it's gonna be like, so this capacitor with its top one was 5 microfarads. I can just find the voltage because it's gonna be whatever the voltage of oh wait, what voltage is it gonna be? It's gonna be the voltage of whatever the 30 ohm resistor is, right? I had to think about that for a second just because it was in a weird orientation. But it's like this problem. It's just gonna be the voltage of whatever that branch is. So it's gonna be the voltage of whatever that 30 ohm resistor is. I put down it's 4.286. So then you could just take those two numbers using this equation, right? You can find the charge of 5 times 4.28. You can find the energy by doing 1/2 QV once you find the charge. So I won't go over that too much, but for this resistor, once you know the voltage, everything else kind of becomes easy. But yeah, for this one, it's going to be the voltage of whatever that 20 ohm resistor kind of initially was, right? Because initially had a, oh wait. Yeah, it's the voltage of whatever that resistor is. So 20 ohm times like 1/7 amps. So that would be 2.57 volts. And I'll show you and then you can just multiply and figure out everything else from there. So I can show you my packet. What I got down, so you can check answers. But yeah, hopefully that's not too bad. Thank you for watching. Have a good one.